Welcome to Nanodium, where small science powers big ideas. In today's episode, we spotlight a remarkable breakthrough at the frontiers of nanotechnology and material science. This is the story of Glaphene, a novel hybrid material born from the chemical union of graphene and silica glass. This discovery not only redefines what is possible in two-dimensional materials, but also sets the stage for entirely new classes of semiconductors for quantum devices, photonics, and advanced electronics. Let's begin with what we know. Graphene, a single layer of carbon atoms arranged in a perfect hexagonal lattice, has been hailed as a wonder material since its discovery. With unmatched strength, exceptional electrical conductivity, and atomic thinness, graphene represents the future of nanotechnology. But while hundreds of two-dimensional materials have been identified, combining them into completely new compounds has remained an enormous challenge. Traditionally, scientists have attempted to stack layers of 2D materials, like cards in a deck. Yet, these stacks typically interact only weakly, with individual layers behaving almost independently. Now, imagine if we could go beyond stacking. Imagine if the layers themselves could chemically bond, creating hybrid materials with properties that neither component possesses on its own. That vision is what a global team of researchers led by Rice University has achieved. They have successfully synthesized Glaphene, the first chemically bonded combination of graphene and silica glass, resulting in a stable, two-dimensional semiconductor with entirely new structural and electronic properties. Satvik Iyengar, the study's first author and a doctoral student at Rice University, describes this as a milestone in material design. According to Iyengar, Glaphene's layers do not merely rest upon one another. Instead, electrons move between the layers, forming partial bonds and creating new vibrational states. These interactions give rise to behaviors not seen in either graphene or silica alone. The result is a material that challenges the traditional boundaries between metals and insulators, opening the door to custom-built semiconductors. The team's method is as innovative as the material itself. They developed a two-step, single-reaction synthesis that begins with a liquid precursor containing both silicon and carbon. By finely tuning the oxygen levels during the heating process, they first grow graphene and then shift the conditions to favor the formation of a silica layer. This precise control was made possible by a custom-built, high-temperature, low-pressure system, a setup that took months to develop in collaboration with visiting Professor Anchal Srivastava from Banaras Hindu University in India. Once synthesized, Glaphene was carefully examined to confirm its unique structure. Working with experts Manoj Tripathi and Alan Dalton at the University of Sussex, the team employed Raman spectroscopy to analyze the material's atomic vibrations. The results were surprising. The spectral signatures did not match those of pure graphene or silica, indicating strong interlayer interactions beyond typical van der Waals forces. Instead of behaving like magnets loosely stuck to a refrigerator door, as is common in 2D stacks, Glaphene's layers were bonded more deeply, enabling unprecedented electron sharing between them. The team further investigated this unusual bonding with the help of Brazilian spectroscopy expert Marcos Pimenta. Initially, an unexpected anomaly in the data sparked excitement, but deeper analysis revealed it to be an artifact, a valuable reminder of the importance of caution, even with reproducible data. To validate their findings at the atomic level, the researchers partnered with Vincent Munier at Pennsylvania State University. By aligning experimental observations with quantum simulations, they confirmed that partial bonds formed at the interface between the graphene and silica layers, transforming the material into a novel semiconductor. What makes this achievement so significant is not just the discovery of Glaphene itself, but the broader implications for material science. Iyengar emphasizes that this method could be applied to create other hybrid materials, combining metals with insulators, or magnets with semiconductors, to design entirely new classes of 2D materials from scratch. As Pulikal Ujjan, a senior author of the study, puts it, true innovation occurs at the junction of hesitation. This work proves that mixing ideas once considered incompatible can lead to groundbreaking advances. The project was a true cross-continental collaboration, involving institutions and experts from around the world. Funding came from diverse sources including the National Science Foundation Graduate Research Fellowship Program, the Air Force Office of Scientific Research, the Quad Fellowship, and Brazilian research foundations. The team has already filed a provisional U.S. patent application to protect the intellectual property behind this novel synthesis method. In Iyengar's words, Glaphene is a material that nature does not create on its own. It is a testament to human ingenuity, and to the power of international cooperation in the pursuit of scientific discovery. If you found this exploration of Glaphene inspiring, don't forget to like this video, share it with fellow science enthusiasts, and subscribe to Nanodium for more in-depth stories where small science powers big ideas. Stay curious, and see you in the next episode.